In this video, we are going to talk about affine ciphers, which will be something that we'll be coding this week as a warm-up to cryptography. Now, in order to talk about affine ciphers, I want to talk about Caesar ciphers, which we saw a little bit of in the first video. The idea behind this is just a shifting alphabet idea, where we have the letters of the alphabet going from A to Z, and then we come up with some sort of shift, say by 2 units. And what we do is we map each element 2 units to the right, except where that becomes problematic, which is at the tail end. And so what we do is we just imagine those things at the end, they're going to kind of circle around and get those values at the beginning that are going to be missing. And that's a great way to visualize this, but one way that we can make this more mathematical is we can make this canonical association between the letters of the alphabet, A through Z, and the numbers 0 through 25 for the 26 letters of the alphabet. And the reason we want 0 through 25 instead of 1 through 26 is because we're thinking like computers, and we're going to ultimately just use modular arithmetic. And we're going to envision this shifting Caesar cipher mathematically as taking an input x, adding 2 to it, modding by 26, which will accomplish taking these ones at the end and spinning them back around to the front, and that will be our output, f of x. So that's a regular old Caesar cipher. We think of there being 26 possible Caesar ciphers. How much are we going to shift by? That entirely determines the cipher. So that might have been good for Caesar's time. However, there aren't that many ciphers. So the question becomes, can we keep the spirit of the Caesar cipher, but get a little bit more mileage out of this and get a few more ciphers? And so I've kind of hinted at where we're going with this. Instead of just adding something to the x, maybe we can multiply the x by something and add something, and kind of have this y equals mx plus b idea going on with the cipher. And so that type of cipher has been thought of, and it is either called an affine cipher, which I think is a little more frequent, or occasionally you'll hear it called a generalized Caesar cipher. So I wanted to give you just examples of encoding and decoding these affine ciphers. Encoding is very straightforward. If you're given an m and you're given a b, I'm going to use an example where m is 3 and b is 1. We take our original letters of the alphabet, we make that canonical association to these numerical values. We multiply them all by 3. Of course, we're welcome to mod by 26 here. Doesn't matter if we mod all at once at the end or if we mod as we go along. So to keep our values in the right range, I've multiplied these values by 3, and at the end I've actually modded by 26 already. We add 1 to each of those values, and then we're done. That's the encoded numerical value. To figure out the encoded letter, we just look up, oh, well, 1 is B and 4 is E, and so on. Now, if we were going to decode that message and we were well aware of the M and the B, what we would want to do is straightforward, at least in theory, and then computationally doing that gets a little bit tricky. We would start with our encoded text, which is a whole bunch of letters, and we'd make that same canonical association with A being 0, B being 1, C being 2, except we're now thinking of that as the output of some sort of encoding mechanism. If we're well aware of our M and our B, to undo the adding of 1, which happened in this step, we would subtract 1. And again, working modularly. So when we get to this 0, we don't want to think about -1. We want to think of cycling back around and getting to this 25 value. And what we would want to do, going from this step to this step, is the undoing of this step to that step, which is to divide by 3. However, that only makes sense in certain situations where you have numbers that are divisible by 3. We have a lot of questions about what would it mean to go from 25 to this spot. If I do a division by 3 and I get 8 1/3, what does that really mean? So I wanted to talk a little bit about that. There's something cool that happens with modular arithmetic. In general, if we're working modulo n, say, only certain multiplications even have the property that they can be undone. So this is a bit of a concern for us. And it turns out that it's the numbers less than n that are relatively prime or co-prime to n that can be multiplicatively inverted. In other words, the only way I'm able to undo a multiplication that happened is if that number is co-prime to the modulus. Now, if you'll remember what it means for two numbers to be co-prime, it means that the only thing that divides both of them is the number 1. For example, numbers like 10 and 21. 10 is 2 times 5, 21 is 3 times 7. So nothing divides those two numbers at the same time except for 1, so those two numbers would be considered co-prime. And what's magic is that if you do have a number m that's co-prime to your modulus, we know for a fact that there exists another number we can multiply m by that has the effect of undoing the multiplication. In our example, what we have is that the number 9, when we multiply it by 3, that gives us an answer of 27. And 27 is, when I mod it by 26, is 1. So if I'm working mod 26, multiplying by 9 is kind of like taking 3 and dividing it by 3, I get back to 1. So here where I had this divide by 3 row and I didn't know what to do on some entries, it becomes much more clear what to do if I instead say, take the previous row and multiply by 9. Now there's no more question about what I need to do in those columns. And the last step is easy peasy. Just do a reverse lookup of these numbers. 17, that's R. 0, that's A. 25, that's Z, and so on. Now where things get more interesting is when we start to think about eavesdropping or cracking codes that we weren't meant to see. So that's the focus of where we'll be heading when we talk about cryptography. How do we prevent codes from being eavesdropped upon? Let's imagine we are the eavesdroppers with this affine cipher. It's really not that hard with a computer to crack an affine cipher. And what are we going to do? Well, there aren't that many Caesar ciphers. There's at most 26 squared of them, and there aren't actually that many. 26 squared is a perfectly fine number of computations for a computer to do. So what we're going to do is search through all of the possible encodings we could have had for a Caesar cipher. We'll try the decoding algorithm on the text we're given, and we'll just search through the words once we've decoded them and see if they are actual words that occur in a dictionary. And if a good percentage of them are, then there's a high probability that we've cracked that code, and that's the method we're going to employ.